Hello all, a very good morning. I welcome you all to the second day of CII International Summit on Corrosion Technology and Management, CII Cortem' 2024. We are delightful to have you here. We will now be beginning with the first session of the day, Corrosion in Rails, Bridges, Highways and Industrial Infrastructure. May I invite our distinguished speakers on the stage, Mr. Haishu Liao, Mr. Satya Prakash, Mr. Mridul Goyal, and Mr. Chetan Raikar. Hello. I request Mr. Haishu Liao to please initiate the proceedings. Thank you.
So the presentation. Thank you so much for the opportunity to come here, and it's a wonderful opportunity. And appreciate all the speakers. We have Satya Prakash, we have Mridul Goyal, and we work a lot in the past, and also here in Mumbai. And then we have Chetan Raikar. Thank you so much, and spend your time here. So now we are in this section 5, talking about corrosion in rail, bridges, highways, and industrial infrastructures. You will see, when we work on highways, right, a lot of highway bridges, and you look looking at, we need to have some codes, like highway bridge design codes and guidelines talking about corrosion, talking about how we attack corrosion. And when we look at the railway and transit structures, and railway, usually older structures, you look at the problems, right? Maybe carbonation problem, but when you look at the transit, nowadays we're talking about transit, talking about urban intensification. So we'll need to develop a lot of transit structures. And then, of course, we have lots of industrial infrastructures. Like we've been doing a lot of Navy facilities, Navy wharf, and lots of corrosion. So we are in the right industry. What's interesting, actually, I'm involved in the Asia business. I come here to Asia area often. I'm based in Toronto, but I cover the Asia business. And I just came from Hong Kong 2 days ago. What's interesting? Well, in East Asia, people try to hide their problem, try to shy away from the problem. And they don't have this kind of a conference. And like they probably talk more private, right? Kind of try to save face. But when I came here and been here a few times, we have all these wonderful international summits. We have a Qualcomm, we have MPP, we have a Cortem'. So it's very good that we raise the awareness. Everyone come together so we know the problem, and then we tackle the problem. So that's kind of interesting because when I was in Taiwan, like a while ago, so they say, well, not like America, where you just present your problem and tackle it. So I think people here in India, it's quite similar to like in North America, and like we just develop the strategy, even national strategy to tackle the corrosion, and then we'll find the best cost-effective way to deal with it. So today I'm talking about a little bit about the concrete structure corrosion mitigation, and then you can see we all come here in like international summits. So we brainstorm all different solutions for the structures. I got a chance to go to Taj Mahal in Agra last year. What's beautiful, what's interesting there is the material there come from all over the world. You can see sapphires from Sri Lanka, you have a jade, a crystal from China, you got some other things from Saudi Arabia, and so when you have the best material, best idea, best thing, best workmanship from all over the world, you will develop best strategy for your infrastructure, right? So that's really good. Okay, let's keep it going. And so I'm more involved in concrete corrosion. So when you look at concrete corrosion, you know, usually the owner wouldn't call us when it's still good. You need to develop a process, a flow for the concrete protection. So usually you see some concrete spalling, concrete falling down, making news. Then we got a call from the owner, and then the consultants then can start to do some evaluation. So you need to look at first of all evaluation, identify the problems first, and then once we know this, the problem, the causes of the issue. So what do we do? Whether we should just demolish it, rebuild, whether we should do some rehabilitation. Yes, rehabilitation, it's our job, right? Once we say yes, and then we got lots of business to do. But when we do rehabilitation, we really save a lot of concrete. We really reduce our carbon print. So once we identify the problem, the causes, then we're looking at a strategy. What do we do? What's the objective? And looking at holding strategy, 5 year. Looking at a long-term strategy, 20 years or 30 years, right? And then you can, once you know your strategy, your objective, usually like owner, consultant, work together to find a strategy, define your objective. And then you want to design for the performance too. And so then you have options. You could do all different options. You can evaluate all different options. They determine what's the solution, what's the best cost-effective way to deal with it. And then now comes to the material selection, right? So then it's quite to the end already, and then we can implement strategy. So of course we need to look at quality control. So we need to look at this concrete preservation process, and then so we have a minimum quality standards, and we're going to get consistent repair, consistent quality. And so we talk about like objective. So whether you want 30 years, whether you want 5 years. So if you want to have say 30 years protection, so then you need to look at say at the end of 30 years, what do you want to have? What's your performance at 30 years? So some of the technologies, say galvanic anodes, you can actually looking at a performance at the end of service life. Then once you have that the performance objective, then you look back, you walk back, calculate. So what you need in the beginning. So it's always good to have the goal in mind, so you can develop your strategy and achieve your performance, the service life. Then the other thing, well, look at the corrosion process, right? Well, say the corrosion, it will take years to develop. Say in new structures, it will take 20, 30 years for the chloride get to steel level and cause the corrosion. And if you could find a way to quickly restore the condition, like repassivate the steel in a few months, and then you can maintain it for the long term. for 10 years, 30 years, it depends on your objective. So that will be good. So we need to look at with the end goal in mind. So then we can develop the strategy, the plan to achieve it. I want to give a little case study because we talk about there's bridges, tunnels, infrastructures. One job I've been working on in Montreal. I've been working on this for 6-7 years now. Corrosion becomes such an important matter there, and what becomes a national importance, right? Like in this job, it's lots of funding coming from the federal, so they hired National Research Council to develop a strategy. So you can see that really becomes a national importance. In this particular tunnel, it's like the most important submerged structure in Canada. At the time, it was built in 1960s. It cost $80 million. Then guess what? Right now, when they finish out the rehabilitation, it's like $2 billion. It's huge. It's top 50 large project in Canada, so it's kind of a national importance. But with the National Research Council involved, so they develop a strategy. So they want, that's important. So they want 40 years without any major maintenance. They want some protection system last at least 20, 25 years or 30 years. And then they can drag on for another few years. They want 40 years without a major rehab. So here's a tunnel. Look at so this actually it's under a river. The problem there is really the de-icing salts in the winter time, spray on the salts, splash on the wall. You see there's 3 salts. 2 salts are the traffic tunnel, lots of corrosion. And the middle salt, that's the service tunnel, and not much corrosion. Then they have they develop a different strategy for different tunnels that will save the money as well. And so we look at this concrete preservation process. So you want to, first of all, you want to identify the issue. So what's the problem there? Cracking, spalling, we see a lot of that already. Delamination, and usually this is like a precast submerged tunnel. So they have a leak, and they have lots of corrosion, it's aged. So they know the issue, and then deal with it. And so, so when you look at a tunnel, say the approaching a retaining wall there, approaching a highway there, it's actually not bad. But when the contractor start to chip concrete, and then you see on the right-hand side, you see all the concrete just coming down. That's why it's very important to do a proper, thorough investigation. Otherwise, by looking at it, we can probably have 5% of concrete repair to do. They repair it, maybe 5 years, they come back to repair again. That's not good. So you need to do a thorough concrete evaluation, and then you know the quantity of the repair. Let's keep going. And even a tunnel, you can see in a tunnel roof and a tunnel wall, a lot of corrosion when they start to do concrete removal, start to chip concrete, and that's where they really want to have a long-term strategy. They want to maintain it for the next 40 years. So they don't want to do major rehab. So they want to find a strategy. So that's why they have a National Research Council to develop a strategy, and then they send out for design build tender. And let's see how it goes. So we need to do evaluation, right? That's a very important part. So diagnose, like in ACI 562, talking about concrete repair, the evaluation is mandatory. You need to evaluate first before you do any rehabilitation. So always good to do this. So you're looking at doing this GPR to find the rebar. You're looking at the chloride contents, looking at the corrosion potential. Once you know the condition of the structure, then you can prescribe some medicine for it. And so, for example, here, we're looking at the chloride contents at the steel level. It's like 0.4% by way of concrete, or about 2.5% by way of cement. It's very high chloride content. Well, because it's important tunnel, they have to live with it. So they need to find a way to live with it. So the corrosion is there, but we need to control it. As long as control, make it slow down to virtually stop. What you stop? Not free, what you stop. And then it will extend the life of the structure. So, in looking at concrete repair, what do? You have different options. And well, in this case, the design build project. So the consultant and the contractor develop a strategy. They need to do surface repair. They need to do shotcrete in some area for like the traffic tunnel. They need to do jackets. And of course, important thing is to provide corrosion protection. They really need to actively control the corrosion. We'll see how it goes. So in the patch repair, you know, we see a lot of this macro soil corrosion in our structures. If we simply just patch back, we're going to see a cracking, delamination, spalling in 5-10 years. Depends on the condition. So that's where you could throw in some galvanic anodes in the patches. It will prevent the problem there. So in the service tunnel, because not too much corrosion, they do have some concrete repair to do. So they could use this patch repair. And then adding this galvanic protection, so they don't have to come back in 5-10 years. So you see all the patches. This tunnel is like about 2 kilometers long. And then now it's a finished service tunnel. And you see that will last quite a while. And then, so that's for service tunnel. But when we look at the traffic tunnel, it's so bad already. Do you want to do a local repair? You want to do patch repair? Patch repair will probably cost you more money than you jacket the entire thing. So in this case, it's probably not worthwhile to do a local repair. It's better to do a jacket or like overbuilds, and then you add in the protection to to all the overbuilds. And in terms of the encasement, galvanic encasements, or the overbuilds, what you could do is you remove some concrete, say remove, depends on the condition, you may remove 20 millimeter, 40 millimeter, or 10 millimeter, roughen the surface, or in some places you need to do, where you have a concrete delamination, spalling already, you need to undercut the steel, go behind the steel. But you're adding another 100 millimeter, so you're adding some new rebar, you're adding some galvanic protection into the overbuilds, so that will give it a long life, like at least 25-30 years. And here you can see the retaining wall, so they overbuild it. You can see they reface retaining wall, and then they add in the galvanic anodes into the reface. And then, inside the tunnel, you see the roof, a lot of corrosion, and then, you see some of the wall already completed, and so they all added this cathode protection there, or galvanic cathode protection. You look at this on the ceiling, on the soffit, and what's interesting there is this is long tunnel, 2 kilometers long, 3 tunnels. They cannot afford to do patch repair. They cannot afford to do piece by piece. So they have this traveling form, 30-meter long traveling form. Each time they pour 30 meter. So each time they do 30-meter repair. They just once they install they remove concrete, they install the new rebar, they install the anodes. So they jack up the traveling form and fix it, and then pump. So that provides a long-term protection. Well, you can see there's, well, people was taking a picture, and I was behind him taking another picture as well. Yeah, picture after picture. But it's really interesting to see this. And look at the ceiling. You can see some places, well, they have spalling, so you go deeper, go behind. In some places, still have a good concrete. You need to roughen the concrete, and then you do your repair. You install the dowel bars, you install the anode, you install the new mass of rebar that will provide the long-term protection. Now it's completed. It's very interesting. You know, the whole thing is like $2 billion, but in terms of the corrosion, it's like $50 million. Even though we're a small piece of the big project, when there's so many big projects out there, even a few percent, 2%, 5%, well, we already get a very good business there already. So I'm pretty sure, well, we are in the right business, we are right in industry, we are in the growing industry. Thank you so much for your attention. Now we're inviting the second speaker, Mr. Satya Prakash, from Additional Director General from Indian Railway Institute of Civil Engineering. Please come.
Thank you very much. Good morning, everyone. Speakers on the dais and distinguished guests. I come from Indian Railway Institute of Civil Engineering, Pune, where we impart training to officers from civil engineering discipline of Indian Railways. As far as I am concerned, I am in railways since last 34 years and worked in various capacities in RDSO, in research organization, as well as Railway Board. And Western Railway, I work in Western Railway. My subject today is corrosion of rails. Actually, I am working as a convener of committee in which we are supposed to suggest the protection measures for the rail, corrosion of prevent rails from corrosion. Corrosion is a big problem for railways, especially in the rails, because it causes the rail fractures. So rail fractures, you know, if the rail fracture takes place, it's a safety hazard. Some of the trains derail and they cause loss of life as well as lot of repairs that have to be carried out and disruption to traffic. So because of that, this is a big problem for Indian Railways. So it's just an introductory topic. We have done some of the work on this, but we request the distinguished engineers and the technocrats present here to give suggestion to us so that we can prevent the rail from corrosion and prevent the rail fractures and the loss of safety, loss of life in case of derailment takes place. So I will just go through my slides, and then corrosion, this we all know, is because of the oxidation of iron which takes place. And iron being ferrosilized, it gets converted into oxide. And then it's basically presence of moisture and the chemicals which aid the corrosion. And it's very It's generally present where the platform lines are there, where a lot of watering take place, and inside the tunnels as well as cuttings. Also the areas near sea coast and the industrial beds, especially those chemicals, those produce chemicals, fumes, there the corrosion is very high. So we have a fastening system on Indian Railways, which is elastic rail clip. And underside of the sleeper is the rubber pad. Then there is a liner. So liner is a big issue for us because the moisture and the chlorides get entrapped in between the rail and the liner. So they cause corrosion. So this is and there is a cyclic loading. So there is a deflection takes place under the liner, between the rail and the liner. So it's continuously in motion. So every wheel gives a motion to it. So it's not static, it's dynamic case. And general corrosion for us is not a big issue because it's about 1.5 to 2 mm thickness, whereas the corrosion is a big issue because it goes to 8 to 10 mm, whereas our thickness of flange is about 12 mm. And if the 10 mm goes, then there is nothing left. So this is the corrosion we can see. Then the fastening corrosion is there because it has seizure. If you try to take out, it will not come out. And when it comes out, if we hammer it, then the sleeper breaks and the liner breaks. So that is a loss. So there is a special process we are adopting is just heating it by the torch and then taking out by the extractors. And this is the, basically we can see here the liner is taken out and we can see that there is a pit corrosion is there. And this corrosion basically in presence of moisture and the chlorides or the chemicals, the corrosion takes place between on the rail, between the liners. And we called it crevice corrosion. And 10 to 15% rail fractures take place due to corrosion on Indian Railways. And the corrosion part is that it's basically a sudden fracture. It cannot be detected in the ultrasonic testing. Unless we remove the fastenings, we cannot see the corrosion also. And the economic part is that 30 to 40% of the premature renewals take place on the account of corrosion every year. Earlier we had toilets which were discharging the droppings on the track. Now that has been completely stopped. Now they are 100% bio toilets. Earlier used to be the microbial corrosion was also present. So they used to eat the iron and make it iron sulfide. And then now there is an effluent discharge from the bio toilets which is containing chlorides. So chlorine is used for disinfection of the effluent. So the moistures along with the chloride now is causing corrosion on the outer side of the rails, which to the lesser extent, but there is an issue. There is a problem in that. So this is another picture of the corrosion taking place. And sometimes you can see the flange has also almost gone. So the measures we are taking is, we are taking measures like we are doing inspection of the corrosion pits every year, measuring the depth of corrosion. We are doing bituminous painting. We are also doing epoxy-based painting and the epoxy coats. But the problem with the epoxy coat is that after some times, due to dynamic action, it peels off. So it doesn't last long. Then we are doing greasing and sealing of the liners to prevent the ingress of moisture and the chlorides. And then we do the shifting of liner bite location. That's not very often now because now we have long welded rails for kilometers together altogether. So it's not possible to shift the liner bite locations. Interchanging of rails is also not possible because they are very long these days. And this is where we do the inspection and do the measurement of corrosion depth by straight edge and feeler gauge. And we do it every year for every 100 sleepers in the corrosion prone areas. Not everywhere, the corrosion prone areas we do it every 100 sleepers every year and record it there in the track monitoring system. And this is the picture of where we do the sealing of liner with the O grade graphite as per IS 408, basically to prevent the ingress of moisture and chemical, and this is done once in a year on the gauge phase side and once in 2 years on the non-gauge phase side. Then we shift the liner location, as it's not very often done, it's not possible now. So this is the bituminous painting we do. This is we do 100 micron thickness, 2 coats at the interval of 8 hours. So we get about 200 micron thickness, and we do this once in a year on outside of the track, outer side of the track, and once in 3 years, once in a year, and outside it is once in 3 years. Then we require drying period of 8 hours. We require surface preparation, and the painting in extreme temperature is to be avoided. Then now we are using 260 meter panels, rail panels. Bhilai steel plant of SAIL is producing 130 meter long rail panels, and they are welding with one joint. They are producing 260 meter long panels. These panels are supplied to the site, and their rail changing is done there. And Railway Board has requested SAIL to do the bituminous painting, but they have explored it, and it's very difficult because 8 hours drying period is not available, because the speed of the rail at the steel plant is 3 meters per second, and doing bituminous painting at such a speed is a challenge, and it's likely to slow down the production. So annual production is of the order of 0.1 million tons. So with that rate, it's not possible, and after the handling, there is chances of damage of the coatings. Then zinc metallizing, we have done zinc metallizing as per IRS specification T51 for zinc metallizing of rails, in which 4 coats of painting. After zinc metallizing, there is a 4 coats of painting, and thereafter, whenever required in service, another coat of painting will be done as per condition basis. This is to be done preferably in the workshop. So we have done this in the flash wet welding plant in Central Railway as well as Western Railway, and we have laid 18 kilometer of track after metallizing. It's a 1.5 year has gone. It's being monitored, but nothing can be said about because it takes time to corrosion to set in. So this is the rails which are produced in 130 meter long, loaded in the special rakes to the sides, and there we are supposed to do the zinc metallizing. So that SAIL is exploring the metallizing of the rails in the plant, but there are issues with it because there are 1 lakh ton, that is 0.1 million tons annual production of the rails, and 30 to 40% of zinc aluminum alloy is wasted. There will be around 800 tons of residue wastage, and that disposal of that is a big issue. And again, it is likely to slow down the production. So we are exploring that. We are also exploring on the linerless fastenings like E-clips and the Waslow clips. And we have also started using high viscous liner that is less hygroscopic. So that uses, it's a repellent of the moisture. So we are hopeful that it will reduce the corrosion. Then we are producing, we have tried with the corrosion resistant rails like copper molybdenum rails. They were initially tried, and about 1,000 metric tons have been laid, and they showed more than twice that of conventional rails, carbon manganese rails. And the problem of weldability is there in that. So welds have to be, there is a post-head weld heat treatment is to be done for about 30 minutes. That's a big challenge in the steel plant itself, because every 30 minutes have to be waiting period. So 2-3 rails will pass. And this is the performance of copper molybdenum rails against the normal. Left side is the copper molybdenum and right side is the normal rails. This is a 3 years, 6 months corrosion exposure. And then we have another corrosion resistant has been developed in industry, academia and user collaboration research project with IIT Kanpur, RDSO and the SAIL. And these rails have been produced, 10,000 metric ton have been laid, and they have shown very good performance in the field. Only issue was their weldability. So the welds now have been developed, but they require 24 minutes of annealing. So that we have to tackle in the steel plant. And we are doing the standardization of welding parameters, and hopefully we will get through this corrosion weldability part, as well as aluminothermic welding of that we will go through. Then we will start producing corrosion resistant rails from the Bhilai steel plant. And we plan to lay them in the corrosion prone areas, especially the coastal areas and the industrial beds. This is the comparative corrosion behavior. NCC rail we call as nickel chromium copper rail. After 6 months of salt fog exposure, it's shown a considerably better performance, corrosion resistance performance. This is the specification of the corrosion carbon molybdenum and nickel chromium copper rails. And the mechanical properties of NCC and copper molybdenum rails is far superior than those of carbon manganese rails. So if the weldability issue is tackled, then we can go for mass scale. So the way forward for us is to get away with the liners, which we are in the process, and use the corrosion resistant rails in the corrosion prone areas, and continue with the existing measures to protect the rails, like bituminous painting and sealing of liners. So we look forward from all the distinguished gatherings here. As I mentioned, I am the convener of the committee which is supposed to required to suggest the measures for corrosion protection of the rails. If we request you to give suggestions, and I have given my email ID as well as mobile number on the first slides. I request again to give the suggestions on that. Thank you very much for your kind attention.
Thank you so much, Mr. Satya Prakash. Wonderful presentation. So we know railway always has some corrosion there. So we're going to have some question and answer later on. But now we get a chance to welcome Mr. Mridul Goyal. And I've been working with Mridul for the last 7-8 years now, right? You come to North America to see me, I come here to see you. So Mridul is still very advanced, a high-level repair contractor. Welcome, welcome.
Thank you so much, Mridul. Hi, good morning. A very good morning to the speakers on the dais, ladies and gentlemen. I represent an industry which is civil engineering infrastructure. And corrosion in this industry has been highly ignored, neglected over the past few years. We have seen, yesterday there was a gentleman from Jindal who was talking about brittle failures on the foot-over bridges. There have been several other. That was one example, but over the past few years, there are numerous examples where concrete structures have failed because of the corrosion in the steel. So I'll run through a brief presentation that I've prepared, a couple of slides about our company, and then we'll get back onto we'll go on to the topic that we are going to discuss. So this is us. We are a 20-year-old company now. We are only into structural repairs, rehabilitation, and strengthening. We are working on almost 19 states in the country. We work on infrastructure, that is bridges and flyovers, industrial plants, water retaining structures, buildings, power plants, marine structures. And we provide a holistic service from diagnostics to corrosion mitigation and strengthening and repairs, which become an integral part of corrosion mitigation service. So coming to the topic of corrosion in RCC structures, many people have talked about it, 4%, 3%, 5%. The truth lies somewhere in between. And however, it's a very, very significant cost for a country like India, which is growing, and this is a waste of a national resource. So we need to keep, there's no doubt that we need to keep these structures serviceable. We need to keep these structures operational for a substantially long period of time, and at least they should meet that 50-year design life for which they are built. So Haishu did discuss on this, so you have taken my thunder on this, but yes, for us to go and understand what really causes the problem in RCC structures and why they fail. So there are mechanical defects, we could call them impacts, overloads, movements, settlements, vibrations, and explosions. So these are one set of causes which create problems in RCC structures. Then you have physical, and they could be the thermal shocks, they could be the freeze and thaw, which happens only in the northern part of our country. But there are shrinkages, erosions, which happen very, very frequently in large water retaining structures, dams, hydraulic structures. And then there are chemical problems, which could be because of the poor choice of aggregates. It could be biological activities, as Mr. Satyaprakash was talking about. They had human waste being discharged on the rails, and that used to be creating problems, not only on the rails, but also on the bridges on which those rails were being laid. And then obviously there is a very vast amount of corrosion. So what is corrosion in RCC structures? There have been perspectives as far as the steel industrial structures is concerned. But so corrosion in RCC is a process which is an electrochemical reaction, and it causes deterioration of steel inside the concrete structure. And why is this corrosion happening in steel, in concrete structures? It could be because of the aggressive environments. So you have a structure like a wharf or a jetty which is built in a sea, marine environment, and you have chlorides in the environment because of the water in which it is built. You would have the aggravated pollutions, and thereby you would have that carbon dioxide, carbon monoxide coming into the structures. We could be using wrong water. So we are, as the country is becoming more and more water scarce, we are diving deep into the Mother Earth, we are boring, we are going deeper and getting very high TDS chloride infested water. Exposure condition of India, unfortunately I do not have a colored diagram or a photograph of this, but apart from the traditionally coastal belt of India, which comes under the severe category, we are now seeing corrosion in the central area, the central part. So just to say, we are doing enormous amount of work in Delhi, which for no reason should be having such vast amount of corrosion. So these are the changing corrosion lines which are happening in India, and particularly in RCC structures. So primary causes of corrosion in RCC structures, as we discussed earlier, could be poor quality of ingredients. It could be the material, either it is coarse aggregates, either it is the sand, water, admixtures. These are some of the reasons which can cause the corrosion of steel inside concrete. It could be improper design specifications. Now, Most of us, as we know, in India, our codes are designed on strength parameters. Durability parameters have been totally missing. The IS 456 doesn't talk about durability to a very great extent, but I think so the newer revisions which are going to come in the future would address these topics of durability of concrete in environments. Then we are going to talk about the faulty construction practices. We see a drawing being issued by the structural consultant talking about aggressive environments as 50 or a 75 millimeter cover, but at site, we find people or the site engineers, supervisors, not very cautious about them. They take it lightly, cover blocks are missing, thereby you having reinforcement very close to the skin or to the surface of the concrete element, and that causes problems. Adding water, excessive water leading to very high amount of water cement ratios, leading to permeability, and therefore the reinforcement gets exposed to the aggressive environments. And then last but not the least, you have this groundwater laden with chlorides being used. So corrosion in steel inside RCC is progressive. And it starts with a circle, which you see the first left photograph, and then it moves to the right and it gets into the spalling. And so there is an initiation time, and which is a substantially long time in any RCC structure where the corrosion is happening inside the steel in the concrete. But then once this initiation time is over, the progression is not linear, it is exponential. And that is where you start seeing the signs of spalling, and where you start seeing those rust marks, and the failures start happening then. So it is upon us to detect, to see, to inspect, and be aware as to what is happening in the steel inside the structures. Now, this is what happens. This is the last stage. You start seeing spalling of concrete in beams, columns, slabs, and this is not the progression, this is not the initiation stage, this is the last few stages of concrete. So I could go on and on various things. You see, this is a cooling tower, the rightmost part, where the hyperbolic portion has actually collapsed. So such is the condition and of the concrete. So what are the solutions? These are the problems that we talked about. Solutions, we have put it in two buckets. One is during construction and one is post-construction. So during construction, obviously, we should be very mindful of the ingredients that we are using. We should be very focused on the supervision. Minor points, small things, we should be keeping the track, taking care of the kind of reinforcement that we use, on the cover of the reinforcement that we do, and then that would take care of substantial part of the problem that could occur in the future. And obviously, we could always add corrosion inhibiting admixtures, which are now very, very easily available. There are multiple companies which are selling them. This would help at least create some passivating layer over the reinforcement. And now coming to the post-construction stage, because we're talking about losses, we're talking about structures which have been built over the last 100, 150 years. So again, during the post-construction stage, depending upon the level of corrosion, the initiation of corrosion, we could be using any of the techniques that have been listed here. And galvanic and ICCP, the induced current systems, are things which are now being used on cases which are extremely aggravated in corrosion. So I'm going to talk about briefly of a project that has been done by us. This is a commercial building in Mumbai, in Andheri. This building was less than 10 years old, constructed, a very high profile commercial building. As you can see from the facade, a lot of nice corporates have offices here. And when we went and we saw, this is what we saw. The basement slabs were post-tensioned RCC slabs, and there was a very large amount of corrosion that could be seen. And when we started digging deep, we found that the PT strands had sheared off. You see some photographs on the left side, that gentleman holding a PT strand which has sheared. Now this is the condition, and you had almost 10,000 square meters of parking area with almost 500 cars getting parked on this parking deck. Somebody had done some amount of repairs without catering for corrosion. They had fiber wrapped a few columns, they had fiber wrapped a slab, and within 2 years, what we see here is that even the repaired area has sheared off again or has spalled because of the incorrect use of the strengthening or design of strengthening mechanisms. So what we did, when we got this job, we said that we're going to be investigating this. And we carried out a very detailed half-cell potential survey. We did almost 2,000 chloride tests, and we created a map which showed us what is the half-cell potential of the entire the slab or the floor. And we also did something which is known as a delta analysis. So we did between the two adjoining half-cell potentials, what is the difference? And so on the right side bottom, what you see, the red marks, the more red contoured plot is the delta plot. So while on the left, if anybody would have read that, we would have found that the corrosion is limited to certain parts of the parking floor. But when you start seeing and analyzing the right part, you see that there is a huge amount of difference in the potentials between those two readings, and that could probably be again aggravating the corrosion. We also did a lot of profiles. So we did corings, and we found what is the level of chloride, how much has the chloride penetrated inside, and we found substantial amount of readings came much higher than the desired. So what you see here is in the slab, what is the depth of the chlorides, and on the right side on the retaining wall at the various heights, what is the chloride ingress. So based on this, we analyzed the entire case, and few of the places we said, no, these are beyond economical repairs, and we said, let's just break them and recast them. That will be a much economical solution. And many places we decided to go ahead with a galvanic protection, because galvanic protection has its own inherent advantages because of installing it and forgetting about it. We don't have to be worried about the rectifiers, the currents being provided on a continuous basis. So multiple kinds of anodes, from a 60-gram anode to 135-gram anode, to a fusion anode which would give a higher current upfront and then convert itself over a period of 3 or 4 months into a normal galvanic anode, was used based upon the findings that we had. So a slab had a different spacing, a wall had a separate spacing, and a different anode was selected. So these are just typical layouts that we drew, and how these were installed by coring, and ultimately, so these are the columns, and various columns got attended by using different kind of anodes. So we also installed at 4 different locations monitoring stations, because we wanted to ultimately prove it to the client that the system that we are installing is going to work. And this is a brief sketch of what a monitoring station looks like, and with the actual photographs. And now we have been monitoring this for around 200 days. So as was understood and as it was designed, the fusion anode, which has lithium cell to give a very high burst of current up front, started off with 7 milliamperes up front, and now it has stabilized over a 200-day period to 2 milliamperes. Haishu talked about 0.4 milliampere as the desired guideline on 12696. But today, after 200 days, this is as of last month, we are at somewhere around 2 milliamperes on this, which is still much higher than the desired. These are the normal anodes, 135 gram anodes. As was again predicted, it would start off with a very, very high current. So this is not fusion. Fusion started off with 7 milliamperes. This started off with somewhere between 1.5 and 2. And now it has stabilized at 1 milliampere per meter square of current being given. So these kind of strategies that have been used provide a definitive and solution to corrosion mitigation of important structures. There are many other structures which require, so that was a case of complete cathodic protection. There are many other projects which are in aggressive environments, and we could look at corrosion prevention. And these are more like precautions where based upon the steel density, the kind of anodes or kind of galvanic protection required or corrosion inhibitors could be designed and could be fixed. These are some of the structures where you see aggressive corrosion, power plants, buildings, marine facilities where we are working, and flyovers. And you see a common problem of corrosion in almost all of these cases which are there. So I'll end with a thought, and the thought being that we must, if we need to conserve the waste of money which is happening on account of losses on corrosion, we must develop a policy to combat corrosion on constructed structures. Currently, we do not have any Indian codes or guidelines as to how and what should be done on constructed structures, how they should be analyzed, what is the basic amount of testing that is required, and how a particular case needs to be addressed. So that is something which, as academia, industry partners, we should all be looking at and doing it. Secondly, again in the constructed structures, in the rehabilitation space, there are many people who are on the dais and people attending this conference. We shy away from performance-based guidelines. We do not address a target corrosion-free service life. Let's say I go into a structure, I rehabilitate it. Do I tell them that I'm going to give you a corrosion-free structure for the next 5, 10, 15, 20 years, depending upon the requirement of the structure or depending upon the balance life of the structure? We do not. And this is something I think so which is from us should get originated, and we should look at giving performance-based specifications. Patch repairs, which have been sort of a problem, they are one of the main issues that we create. And we go into a structure, we intervene, we do patch repairs, and we find sooner rather than later, then you have an adjoining patch, which Haishu again talked about being as the ring effect or the halo effect, and you have the adjoining concrete getting spoiled maybe in 2, 3, 4 years of time. And lastly, somebody talked about Japan and somebody talked about 1% as the annual loss of corrosion. If we could target even 0.1% or 0.05%, we were talking with doctor yesterday, and we were talking about 0.05% reduction, I think we would have achieved substantially. So thank you all for listening, and have a great day ahead. Thank you.
Thank you so much, Mridul. A wonderful presentation while talking about performance-based corrosion specification. It talks about the how you can develop a strategy with minimum cost to reduce the repair costs and damage. And now we get a chance to invite Mr. Chetan Raika. Mr. Riker is the chairman and managing director from Structural Designer Consultants. I just talked to Chetan just now. Well, Chetan was actually designing this building, rehabbing this building as we speak right now, right? It's been working on this for the last many years, right? And please.
Thank you very much. Good morning, all. I knew there are so many experts sitting here. They would be talking of corrosion, why corrosion, how to mitigate. And then I started thinking, what do I have to contribute on corrosion? Because I am on the second day, luckily on the first session, but the last speaker. And when other batsmen have batted well, you hardly have any scope to make any runs. Friends, I am a consulting engineering background, civil engineer, second generation. It's a close to 57-year-old organization fighting with corrosion for all 57 years. But we are also into new construction. And I will have a few slides to show you. And I'll quickly go through them because I want to chat more on the last slide that I have today. Before the thank you slide, of course. But marine structures. We are a few meters away from sea while we are seated here. And who can know more of corrosion than Mumbaiites? We have been fighting corrosion left, right, center because of the marine environment, the pollution, the humidity, of course, which is because of marine environment. Let me quickly run through all these slides. We are not only talking of industrial structures, we have so many heritage structures, like currently the one which we are sitting in. And as Mr. Leo introduced me, I am the fortunate consultant who is restoring the structure, this very structure. The scaffolding that you see outside, the inconvenience is because of me. But you have so many marine forts. I see a few people in uniform. They must be fighting corrosion day in and day out. Forts, refineries, jetties. Alternative wetting and drying, temperature change, impact of vessels, chloride, sulfate, AAR, that is alkali aggregate reactivity. Luckily, I have a color slide, Mridul. But the source is NML, Jamshedpur. But this slide is very important. I slightly beg to differ with you, Mukul, when you say that Delhi also has challenge of corrosion. Yes, Gurgaon has challenge of corrosion, but that's use of, in fact, you answered in one of your slides that use of subsoil water, which is brackish, is the cause of corrosion, I believe, in Gurgaon, or Gurugram as the new name is, because that has been traditionally an agricultural land. So much of nitrates and phosphates and other salts have gone into that. So the subsoil water is contaminated with all the salts. And if you use that in concrete, what do you expect the poor concrete to do? Protect your steel? No. Less than 5 or 10 years, it shows that I'm incapable of protecting. I'm capable of taking the load, but incapable of protecting your steel. So the buildings in Gurgaon are crumbling. But it's not, when I say I slightly beg to differ with you, Mridul, it's not that the demography of corrosion is not changing. There are some pockets where, because of not following the good engineering practices or the standards, there have been cases of corrosion. There have been cases of earthquake. In Gujarat earthquake 2000, more than 10,000 structures collapsed. Who is responsible for it? God? No. It's civil engineers. They didn't design as per the standards. Same way. Corrosion is needed to be stopped at the construction stage itself. Of course, there are many people who are offering solutions to corrosion, and they will kill me after this. But I would still go to say, let's put them out of business by making structures which do not require corrosion protection. And they also will be happy, very happy, I'm sure, that we are trying to achieve less than 1%. Well, it's a very ideal situation. Corrosion and cancer are similar. it's a, how could I say? It's bad change in your own cells. It's unwanted, your cells going bad. Cancer also does not come from outside. It's your cells behaving differently. Corrosion also is the same. Of course, it's because of the external factors. You have stress-induced cancer, you have stress-induced corrosion. You smoke, pollution goes inside, and you have cancer. There is pollution outside, you have corrosion. So corrosion and cancer are comparable. Second point, what I want to make here is, if you study human body, God has given us hands, and they can reach every part of your body. They can reach here, here, top to toe, everywhere. Why? He has built your body as maintainable. Some parts are difficult. If I have to scratch my back, I have to strain a little. But my request to the designers here is, please make maintainable structures. I'll show you some of the next slide. The challenges is access. The jetties, if you have to inspect, even inspect the underside, is a big challenge. You need, the cost of access is more than the cost of inspection team. Something needs to be done about it, high time. Inspection underwater. Most of the water in India is so turbid that inspection underwater is practically impossible. I'm not talking of the Lakshadweep and other this is. I'll have a case study of where there is clear water also. Non-availability of technical data is a third challenge. Limitations on NDT. There are 15, 16, 20 non-destructive testing techniques. I have been using them for almost 40 years now. But I find them quite limited. It's not God. NDT is not God. See, these are few of my engineers struggling for inspection in a very dangerous way. If you see this guy, I do not know the top right, the person in blue shirt, whether he was trying to commit suicide or something. I shouldn't be showing this in a safety forum, otherwise I would be thrown out of. But just look at this. These are very dangerous situations in which the team is struggling to work. So the challenges of inspection. Can you see the top left photo? They are in a shoe. This is Indian innovation. So we use anything and everything to save cost of access. But what if I had designed the structures where easy access was permissible? Maybe these costs were not required to be incurred. I'll go a little fast. 15 minutes is the time I take to brush my teeth, not speak on corrosion. So it is. So it's, see, poor light. See this, poor light. If I have to take the electrical light under the bridge, what can I do about it? I don't have a solution to every situation, but I am sure there are so many brilliant people here who will. The distance, if I have to inspect a perennial bridge or a jetty, the distance is killing. Training. There are no trained inspectors, my dear friend. In India, the course of repairs, maintenance has been introduced just 5 years back. Just 5 years back in engineering colleges. I don't have knowledge of other universities across the world, but this subject is being formally trained only for 5 years now. It's high time. So we don't have trained engineers. Major training is needed to do inspection, to identify the root cause. To identification of root cause is a major challenge. Trained eyesight, supervision. I think we need people with supervision. Documentation and photography. We Indians are poor at documentation, or we are shy of documentation. We need to come out of both. And let me go a little fast. This is what underwater inspection, if I can show you. See the quality of water on the left bottom, this thing. It's turbid. So you can't see less than below a foot of water depth. Even if you take videography, photography, you can't see anything. You put divers and they are not able to see, so they just touch something and come back and give you some data, which is not very useful. I have done diving myself with the hope that I could see something myself, but these are the some of the causes. Let me go fast. Case study 1, refinery. Refinery does have a major challenge of corrosion. They have jetties, they have corrosive environment, and they have very, very tight maintenance schedules because it's a 365 days, 24/7 operation. It's a continuous operation. So the schedules of maintenance are very, very tight for only few hours. And maintaining a structure for corrosion is a big challenge. Let me go a bit fast. Jetty also is mota moti the same. Mota moti in English is by and large. I can go on and on and on showing you corroded structures, because as I said, practically we have been trying to give a solution for almost 57 years now. We have not been able to offer a good solution to corrosion, and I have been in practice for 37 years and I have not been able to give a good solution to corrosion. Because if we talk of a jetty which is supposed to last 100 years, 120 years, and we offer a solution for 5 years, 10 years, is that right? No, I don't think it is. This is how our bridges, this is a photograph of some Mumbai bridge or a dumping yard. And the same garbage is being burnt by people. While you burn, the concrete burns. And concrete beyond 350 degrees is rendered useless for load carrying capacity. Corrosion. Why do structures corrode in less than 5-10 years? Multi-storied structures, 50 years, 50-story structures, 60-story structures in less than 5 years built by the best of developers today in Mumbai are corroding. Why? It is definitely ignorance and poor quality construction. Or maybe use of bad steel, re-rolled steel, so many these things. But these are all, we are just trying to find faults and not improving on them. Very unfortunate. Now this leaking thing is lack of maintenance. We go and buy a toaster of 1500 rupees. It comes with a warranty of 3 months and a maintenance manual. You build a bridge of 1500 crores and there is no warranty. The very next year it starts cracking and crumbling and there is no maintenance manual. It's high time that construction industry starts making maintenance manuals for every structure that they create or construct. Because structures like this are created, we construct. We don't create anymore. That's again one more subject of my interest. Let me run very quickly. Now this is a marine resort. We have been doing quite a few of them in Maldives. The water is so nice and the place is so nice. First couple of them I visited myself and my team said, boss, you can't be going to the nicest places at company expense. Allow us to go. So now my engineers go there. But a 7-10 feet of water is so clear. You just do little bit of snorkeling or have a gadget and go down, inspect yourself. Corrosion is there too. They have a challenge of corrosion. Even Maldives with the best of zero pollution or whatever we can call it, has corrosion challenges. Less than 10 years, 20 years also, they have corrosion challenges. So pollution is one of the reasons. Marine environment, the salts and the humidity is, I believe, a major cause. Construct and design structures with maintenance in mind. This would be my first request to all the designers here, those who are creators, whether it's railways. Satyaprakash sir gave a fantastic, it's a fight that railway is putting up with corrosion. And the challenge is, I think India has the largest rail network today in the world. So that's a challenge. So can we make structures which are, nothing is maintenance free, I believe. Even a Rolls-Royce machine needs maintenance, but at least know how to maintain it. When we talk of civil structures, do we know how to maintain them? Do we specify how to maintain them? Probably there's access, ease of maintenance, preventive maintenance, and not wait for breakdown maintenance. There are more Indians, so I would request the overseas guests to just shut down because I'm talking of the Indian mentality. You know, when we go to a mechanic and he says, sir, the clutch plate of your car is kind of wearing out, another 6 months' time it may give way. We don't do preventive maintenance. We go and tell him that it's still 6 months, no? I'll come back when it breaks down. Hey, only my overseas guests are laughing here. I think we also need to not laugh at it, but change our mentality. When we go to a doctor and doctor says your cholesterol level is high, your BP is on the threshold, you stop booze, stop non-veg, stop fried. We say, okay, it's still at the brink, no? I will come to you when it crosses and give me some medicines while still not stop. So we need to come out of this thought process of breakdown maintenance. We need to think of preventive maintenance very seriously if we really want to save country's money. Otherwise, the chal raha hai, things are happening. Maintenance manual for each structures. Use richer specifications. In Hindi, there is a saying, Sasta roye bar bar or mehenga roye ek bar. In English, it is that if you buy a costly stuff, there are better chances that the stuff is genuine and good. Costly stuff can be bad, but the cheap stuff can never be good. So if you try to economize in the construction, then there is a possibility that you are expecting early maintenance. So it's wiser to spend a little extra, maybe 5% extra cost during construction, and save the structure, reduce the maintenance as much as is possible. Prevention is better than cure. That's the only thing I would like to say about corrosion. And the next is, thank you very much for listening to me patiently. Thank you.
Thank you so much, Mr. Riker. A wonderful presentation. Well, so now we have completed our presentation, and we really appreciate you guys coming here, take your time. So we all coming together, we brainstorm the ideas, we share experience. So we still have a few minutes for 2 questions. So I guess because we have lots of things to share, right? That each of us, we can probably speak for the whole day, and we need to stay here another 4 days, right? But we only have so much time here, but we always run out of time. So we got 1 question, so we have only 2 questions. Yes, can somebody get the mic? Okay, 2 questions.
Yeah. Hi, good morning, everyone. My name is Jayant. I'm from L&T Energy. Thank you for those wonderful presentations. My question is to Satyaprakash sir. Sir, thank you so much for the presentation. I myself got to learn so much. I mean, especially the one where you told that we have changed it to the bio toilets. And you have reduced the entire, to remove the MIC corrosion itself. So now my question is, over the last 2 days, there have been a lot of talk, about moving away from the traditional carbon steel. Obviously, now when it comes to railways, you operate along the length and breadth of this country. And we have also seen a lot of speakers presenting the corrosion map of India. So my question is, going forward, you have told that the future will be to go with corrosion resistant rails. So is there still a chance, or within this entire landscape of our country, where we can use carbon steel rail as the material of choice, because there may be areas where the corrosion is not so extreme. And do you think will it sustain for the service life?
Actually, carbon remains the basic alloying element. So the elements which are added are microalloys. Nickel, chromium, copper are the microalloys. Even the molybdenum is also microalloys. They will remain there. Carbon will remain there. But those chromium and copper are basically have the weldability issues. So that is why carbon rail will continue. Carbon manganese rails will continue. And now we are going in for the higher strength rails of 350 HT rails, 1175 megapascal rails. And those are also heat treated rails. So my answer is that they will continue, but only we need to do microalloying. Thank you.
Thank you, sir.
Yes, I'm Nicole Kinsman with the International Molybdenum Association. I was wondering for Mr. Goyal, maybe also the last speaker, about stainless steel reinforcing bar. You didn't mention that at all. Are you considering that in your evaluations? At least I think what we do other places is to just partially, in the outermost layer, use stainless steel to make it economical.
Yeah, we have been using stainless steel for last almost 2 decades in important structures like public utility structures, retaining walls. Recently we did governor's residence, which is bang on the sea, the state of Maharashtra. So that also, there also we used stainless steel. And we are also looking at structures with other types of steels, but the economy is a challenge as of now, and also easier availability, you know, because sites are sometimes congested. So if the stainless steel manufacturer tells me you buy the entire lot, I don't have the space to keep, and those kind of challenges we are trying to make. But we are using stainless steel for almost 2 decades now, and other types of steel also. If I'm given 60 seconds more, I'll give the Ayodhya Ram Mandir, which was inaugurated on 22nd of January, is designed, the Ayodhya Ram Mandir, which was opened on 22nd of January in Ayodhya in India. Are you aware of that temple? It is designed for 1,000 years of serviceability, and the entire structure is constructed without reinforcement. What does it show? It's not, see, it's, the world is so scared of corrosion that they even opted to avoid use of steel for durability. I think it's a defeat of the steel industry that we are not able to give. I think Darji has some other viewpoint. Maybe you can say that. So that's that. Later, over a cup of tea, sir.
May I have one question? Yeah, it's okay. I can only add one more thing to this.
Yeah,
I have one even in the rehabilitation space, the industry which I primarily work, we have started using stainless steel rebars. We are also substituting steel reinforcement, whether carbon steel or stainless steel, to FRP bars. So that is also now Indian Roads Congress has published a code which has now started allowing us to design using FRP bars, and they are a little more, noble, would not corrode because there is hardly any, there is no steel inside. And so that's probably the way forward for more important structures in the days to come.
Yeah, I have one question, sir.
Sorry, I think we're run out of time. So I really appreciate everyone. So hopefully you get some takeaway.
The question is to Mr. Mridul Goyal. You have showed the half cell potential mapping. Okay, so what I'm surprised, the potential ranges are from, I think, 350 to minus 220. But I think the rebar corrosion, if you look at the copper sulfate reference, is around minus 660. So you said that the red zone is not dangerous.
What I said was, when you do a corrosion mapping just using the copper sulfate half cell potential readings, you get a certain reading,
Correct.
right? And then based upon the Indian codes or any international codes, you say that minus 350 volts or lower is where you have a higher susceptibility of corrosion. So you plot a simple graph and you would have minus 350 and lower marked as deeper red, and as you go lower than that, you would turn it to green.
Okay,
right?
what all that you showed, the red zone is
Yes, minus 350 and lower.
lower.
And lower, right? But then what is more important is that, let's say I have a 500 square meters of slab, and then on one particular area I am getting a minus 400 reading, and right adjacent to it, in less than a meter where you take the next reading, you're getting minus 200. So now the corrosion potential difference between those two areas. So this in my first map was green, because it is as per
That
the
was
code.
the difference.
Yes, and because now the delta between the two.
Okay, delta of these two.
Yeah. So that is what is going to drive my corrosion current,
Fine,
and this would become my next susceptible area.
Thank you, thank you.
Thank you so much. So hopefully you get some takeaway. So my takeaway here, I am from Mr. Goyal, Mridul Goyal. So we need to look at repair durability. So we need to look at long-term service life. And my takeaway from Satya, yeah. So, well, we need to do proper maintenance. Like every 3 years, we do some maintenance. Every 5 years, we do some maintenance, right? And inspection too. So, my takeaway from you is, well, we need to look at, when we design new structure, we need to look at the access. How do we access in the future? We need to make a maintainable structure. So, and we do something right now, it will save us for the long term. Thank you so much for attending this session. This concludes our session right now. Thank you.
We will now have a small ceremony of handing over the mementos as a token of our gratitude. Requesting Mr. Haishu Liao to please present the memento to Mr. Satya Prakash. Requesting Mr. Haishu Liao to please present the memento to Mr. Mridul Goyal. Requesting Mr. Haishu Liao to please present the memento to Mr. Chetan Raikar. Requesting Mr. Satya Prakash to please present the memento to Mr. Haishu Liao. I thank our esteemed speakers and may I request our guests to join us for networking tea coffee. Requesting everyone to please be back by 11 o'clock so we can proceed with the next session on time. Thank you.